Welcome back, everybody. Ready for another deep dive?
Always.
Today, we're going to be looking at the science behind some everyday things, things we see all the time but might not really think about. Stuff like blue skies, clouds, rainbows.
Yeah, the familiar stuff can actually be the most complicated when you really dig into it.
Exactly. So let's get started. First up, that big blue thing above us. Why is the sky blue? I mean, it's not just empty space up there, right?
Nope,
Yeah.
definitely not empty. It's all about sunlight. Sunlight looks white, but it's actually a mix of all the colors of the rainbow, each with a different wavelength. And blue light, because it has a shorter wavelength, well, it gets bounced around more by the air molecules. Kind of like if you threw a tiny ball at a bunch of obstacles, it would ricochet all over the place, right?
Yeah. Okay, so the blue light is bouncing all over the sky.
Exactly. It's called Rayleigh scattering. All that scattering is why we see blue when we look up.
So what about sunsets then? Why all the reds and oranges when the sun goes down?
Think about it this way. When the sun's setting, its light has to travel through a lot more of the atmosphere to reach us. That longer path means more of those shorter wavelengths, like blue, get scattered away.
Hmm.
So what's left? The longer wavelengths, like red and orange, they make it through to our eyes.
It's like nature's light show. Beautiful. Okay, let's talk about clouds now. They look so light and fluffy, but I bet they're not what most people think they are.
Right. You'd never guess they're actually made of millions, maybe even billions, of tiny little water droplets, or sometimes even ice crystals.
Really?
Yeah, and those form when warm air, the kind that's full of moisture, rises and cools down. And as it cools, well, it can't hold all that water vapor anymore.
Like a sponge that's completely full.
Exactly. So that extra water vapor has to go somewhere. It condenses, forming around microscopic particles in the air like dust or pollen, even tiny bits of sea salt. And there you have it. A cloud is born.
I never knew that. But here's what I don't get. If clouds are made of water, even ice sometimes, how do they stay up there? They have to weigh a ton, right?
Oh, they do. Clouds can weigh tons, literally. The secret is that all those tiny little droplets are spread out over a huge area. Plus, they're caught in these rising air currents, that help keep them aloft. It's kind of a balancing act between gravity pulling down and the air pushing up.
Wow, that's pretty cool. Speaking of things falling from the sky, how does rain happen? When do those cloud droplets finally decide to come down?
Well, it all comes down to size and weight. As those little droplets bump into each other inside the cloud, they start to combine. So they get bigger and heavier, and eventually they get so heavy that the air currents just can't hold them up anymore. And that's when we get precipitation. Rain, snow, sleet, hail. It all starts with those tiny cloud droplets.
So fascinating. Most people probably picture raindrops all wrong.
Oh, you mean the classic teardrop shape?
Yeah.
Turns out that's not quite accurate. Raindrops actually start out as tiny spheres, and then as they fall, the air resistance flattens them out a bit. So they end up looking more like hamburger buns than teardrops.
Okay, that's a way better visual. I'm never going to look at rain the same way again. Let's move on to something a little bit more intense. What about thunderstorms? Where do those sudden downpours and lightning shows come from?
Thunderstorms are like nature's superpowered elevators. You need warm, moist air rising really rapidly to create those towering cumulonimbus clouds.
It's amazing how fast those clouds can build. What's happening inside them to cause all that commotion?
Well, it's all those rapid updrafts and downdrafts. They're like the engine of the storm, causing all those different particles inside the cloud to collide. And those collisions create static electrical charges.
So kind of like when you rub a balloon on your hair.
Yeah, exactly like that. And when enough of those charges build up, you get a sudden release of energy, a massive electrical discharge. That's lightning. And it's so powerful that it can heat the air around it hotter than the surface of the sun.
Wow, that is intense. What about the thunder? Is that a separate thing or is it caused by the lightning?
It's all connected. See, that incredible heat from the lightning bolt causes the air around it to expand incredibly quickly, like super fast. And that creates a shock wave, which is what we hear as thunder.
So the lightning comes first and then the thunder follows.
Exactly. Here's a fun little trick. Next time you see lightning, count the seconds until you hear the thunder, divide that number by 5, and you'll get a rough estimate of how many miles away that lightning strike was.
That's a cool tip. All right, let's talk about the really big storms now. Hurricanes, typhoons. Are they just really, really big storms or is there something more to them?
They're definitely more than just big storms. They're actually entire weather systems fueled by the heat energy of warm ocean water, like a giant engine powered by warmth.
So how does that engine get started?
Well, you need a big area of warm ocean water heating up the air right above it. That warm air, full of moisture, starts to rise. And as it rises, it creates a low-pressure zone at the ocean's surface. That low-pressure zone is like the seed of the cyclone.
Okay, so you've got this low pressure zone, then what?
As that warm, moist air rises, it cools and condenses, forming clouds and releasing even more heat. It's like a self-feeding cycle, and it can create incredibly powerful winds and torrential rain.
And we can't forget about the Coriolis effect, right? That's what makes those storms spin.
Exactly. The rotation of the Earth actually causes that rising air to deflect. In the northern hemisphere, storms spin counterclockwise. In the southern hemisphere, it's clockwise. Crazy to think that something as massive as the Earth's rotation gives them their spiral shake.
So many ingredients have to come together just right to create these incredible cyclones. It's amazing. But speaking of amazing weather phenomena, let's switch gears and talk about deserts. Most people probably just think dry and sandy, but I bet there's a lot more to it.
Oh yeah, deserts are way more complex than they seem.
Oh.
One of the key factors is descending air. See, unlike those rainforests, where you have all that warm, moist air rising, deserts often have sinking air. That sinking air creates high-pressure systems.
Okay, so the opposite of what's happening in a rainforest.
Exactly. And as that air sinks, it compresses and warms up. It literally sucks the moisture out of the environment. That's why deserts are so dry.
So it's all about where that air is moving up or down. Fascinating. But not all deserts form the same way, do they?
Nope. Take rain shadow deserts, for example. They form when most air runs into a mountain range.
What happens when the air hits those mountains?
Well, the air is forced upwards, right? As it rises, it cools. All that moisture it was carrying starts to condense and falls as rain or snow on one side of the mountains. By the time the air makes it over the top and starts to descend on the other side, it's bone dry. That creates a desert in the shadow of the mountains. The Mojave Desert is a great example of that.
Wow, so those mountains act like giant walls blocking all the rain.
Basically. And of course, distance from oceans plays a role too. The Gobi Desert, for example, it's so far inland that any moist air coming from the ocean has already lost most of its moisture by the time it gets there.
It's like a giant moisture tug of war. Okay, so we've got blue skies, we've got clouds, we've got deserts. But no deep dive into weather would be complete without talking about rainbows. They're so simple and beautiful, but I bet the science behind them is pretty cool.
It is. Rainbows are all about how light interacts with water droplets. So when sunlight enters a raindrop, it bends, we call that refraction, and it also splits into all its different colors.
It's like shining a light through a prism.
Exactly. Then that light bounces, or reflects, off the inside of the raindrop and bends again as it exits, creating that arc of colors we see in the sky.
So each color is bent at a slightly different angle.
Precisely. And get this, no two people actually see the exact same rainbow.
What? How is that possible?
Because you're each seeing a slightly different set of raindrops, creating a unique arc just for you. And those fainter secondary rainbows you sometimes see above the main one.
Oh, yeah, those are cool. What causes those?
Those are formed when light reflects twice inside the raindrops. And that reverses the order of the colors, which is why they look different.
It's like nature's giving you a personal light show. It's incredible how much science is going on above our heads every single day.
It really is. We take so much of it for granted.
Well, we've covered a lot of ground already. Blue skies, deserts, rainbows. But we're just getting started.
That's right. Let's move from the things we see to something we can really feel.
You mean?
Wind. Next up, we're going to dive into the power of wind and all the ways it shapes our planet.
Yeah, wind. It's more than just moving air. It's a real force of nature. Shapes landscapes, drives those ocean currents we were talking about, even influences global weather patterns.
I've always wondered what actually causes wind, what gets it moving in the first place.
It all comes down to differences in air pressure. Basically, air always wants to move from areas of high pressure to areas of low pressure, trying to even things out.
So it's like water flowing downhill, always trying to find that level spot. Exactly. And the bigger that pressure difference is, the stronger the wind's going to be. And there's a whole bunch of things that can cause those pressure differences, like how the sun heats the earth, or those big weather systems we talked about earlier.
Let's talk about the sun for a minute. I mean, everyone knows it heats things up, but how does that create wind?
Well, the sun's energy doesn't heat the earth evenly. Different surfaces absorb and reflect sunlight differently. Like land. Land heats up and cools down a lot faster than water does.
Oh, I see. So you end up with these patches of warm air and cool air, and that's where the pressure differences come in.
Bingo. Warm air is less dense, so it rises, creates an area of low pressure. And that cooler air, well, it's denser, so it sinks, creating an area of high pressure. And remember, air flows from high to low pressure. So there you have it, wind.
Like a giant convection oven circulating air all over the planet.
I like that analogy.
Hmm.
And it's not just about those local winds you feel. It's what drives those massive weather systems, too.
Like the high pressure zones we were talking about over deserts.
Exactly. And the low pressure systems that bring storms. They create these huge pressure differences, gradients, and they can push winds across vast distances.
Wow, so even those gentle breezes on a summer day are part of the same system that drives those hurricane force winds.
It's all connected. And then, of course, you have to factor in the Earth's rotation.
Oh yeah, the Coriolis effect. But does that really affect wind? I mean, it's not like I can feel myself being flung sideways because the Earth is spinning.
Right, it's not something you really notice on a small scale, but it does make the wind curve. In the northern hemisphere, winds curve to the right, and in the southern hemisphere, they curve to the left.
So that's why those global wind patterns aren't just random, right? There's a pattern to it all.
Absolutely. You've got the Coriolis effect, the pressure differences, the uneven heating from the sun. It all works together to create those predictable wind patterns, like the trade winds that blow towards the equator, or the westerlies that blow across the mid-latitudes.
So it's not just chaos up there, there's an order to it. That's pretty amazing. But all that wind moving around, it's not just about the weather, is it?
Nope, it affects our oceans too. Big time.
How so? I hadn't really thought about that connection before.
Well, wind is one of the main things that drives ocean currents. As wind blows across the surface of the ocean, it creates friction. It's almost like the wind is dragging the water along with it.
So the wind is like an invisible hand pushing the oceans around the globe.
I like that. And this isn't just happening on the surface either. Those wind-driven currents can go down thousands of meters deep,
Yeah.
constantly churning and circulating huge amounts of water.
And those ocean currents are important, right, for more than just making waves.
Oh, they're absolutely crucial. They carry heat energy from the tropics towards the poles, which helps regulate temperatures across the globe. They also affect weather patterns, marine ecosystems, even how nutrients are distributed in the ocean.
Wind is definitely a lot more powerful than I ever gave it credit for.
For sure. Speaking of powerful forces, wind also plays a key role in something else,
What's that?
the water cycle.
Oh, yeah, the water cycle. Oh, we touched on that a bit when we were talking about rain, but what exactly is it again? It's been a while since my school days.
Well, think of it like a giant loop. Water is constantly moving all over the planet, going up into the atmosphere, falling down as rain or snow, flowing over the land, seeking into the ground. It's a never-ending cycle.
And it's all powered by the sun, right?
Right. The sun's energy heats up water on the Earth's surface, making it evaporate and rise into the atmosphere as water vapor. That water vapor condenses to form clouds, and then eventually we get precipitation.
Right, and that precipitation refills all the water sources on land, rivers, and lakes, and it all flows back into the ocean, and the cycle starts all over again.
Exactly. And of course, wind plays a big role in moving all that water vapor around. It influences where clouds form and where all that rain or snow falls.
It's amazing how much is going on all around us, all the time. But okay, so we've talked about the science behind weather, but how do we actually predict it? How do scientists study and forecast these complex systems?
Well, that's where meteorology comes in. Meteorologists are the scientists who study the atmosphere and try to figure out what's going to happen with the weather.
So they're the ones who tell us whether to pack an umbrella or wear sunscreen.
Well, that's part of it, but it's a lot more complicated than that. They use all sorts of sophisticated tools like computer models, satellite images, weather balloons, radar, and they gather tons of data to make sense of these patterns.
Sounds like a pretty tough job.
It definitely is. You need a strong understanding of physics, chemistry, math, computer science. You have to be a good thinker and a good communicator.
So what are some of the toughest things about predicting weather?
Well, weather systems are constantly changing, and there are so many factors at play. Trying to make accurate predictions, especially long-term ones, is really difficult.
Yeah, I can imagine. It's like trying to figure out where a billion bouncy balls are going to land after you drop them all at once.
Uh-huh. Great analogy. And the challenge is even tougher with all the changes happening to our climate.
That's a good point. Climate change is a term we hear all the time, but people often confuse it with weather. Can you clear up the difference?
Sure. Think of it like this. Weather is what's happening outside right now. Is it sunny? Rainy? How hot or cold is it? Climate, though, is the long-term average of weather patterns over a certain area.
So weather is like a snapshot and climate is the whole photo album.
Perfect. Weather can change from one day to the next. Climate, though, changes over much longer periods. It's about long-term shifts in things like temperature, rainfall, and all those other things we've been talking about.
And when we talk about climate change, we're talking about changes to those long-term patterns that are happening globally, right? Primarily because of what humans are doing.
You got it. Scientists overwhelmingly agree that human activities, especially burning fossil fuels, are releasing these greenhouse gases into the atmosphere. And those gases trap heat, causing the Earth's climate to warm up faster than it should.
And we're seeing the effects of that already, right? Rising sea levels, those crazy heat waves, changes to where plants and animals can live.
Climate change is a big deal, and it will affect everything. And the science is clear.
Okay, so how do scientists even study something as huge and complex as the Earth's climate?
They use all sorts of methods. They analyze things like ice cores from glaciers, tree rings, layers of sediment from the ocean floor. These things give clues about past climate conditions. And they use these super complicated computer models to simulate the Earth's climate and try to predict what will happen in the future.
It sounds like a huge team effort.
Definitely. It takes experts from all kinds of fields: atmospheric science, oceanography, geology, biology, computer science. It's a massive collaboration.
And it's all focused on understanding how our climate is changing, what those changes mean for us, and what we can do about it.
Exactly. It's a huge challenge, but there are a lot of brilliant people working on it, finding solutions for a better future.
Okay, I think we need to take a break from all this serious stuff for a minute. We talked about rainbows earlier, but what about those other cool things you see in the sky? Halos, sundogs, glories, those are so beautiful.
They really are. Those things are all about how light interacts with ice crystals in the atmosphere. Those tiny crystals act like prisms, bending and reflecting light in all sorts of cool ways.
So it's kind of like how rainbows form, but with ice instead of water.
Exactly. The shape of those ice crystals and how they're oriented, that's what determines what we see.
So how about halos? What causes those rings of light you see around the sun or moon sometimes?
The halos usually form because of those hexagonal ice crystals way up high in the atmosphere in cirrus clouds. The light passes through those crystals and gets bent, creating that halo effect.
And what about sundogs? Those bright spots on either side of the sun.
Sundogs, sometimes called parhelia, they're also caused by those hexagonal ice crystals, but they're lying flat, horizontally this time. So light passes through them and gets refracted horizontally, which creates those bright spots.
It's like those little ice crystals are mini lenses, focusing the sunlight.
That's a great way to think about it. And sundogs usually appear at a 22-degree angle from the sun, because that's where the light bends the most.
So cool.
Hmm.
What about glories? Those colorful rings you see around your own shadow, like when you're up on a mountain or in a plane?
Glories are a bit more complicated. They involve both refraction and diffraction of light. It usually happens when sunlight is hitting clouds below you, and that creates the circular rainbow effect around your shadow.
It's like nature's putting on a special show just for you.
Yeah. All of these, the halos, the glories, they show us that the atmosphere is way more than just air. It's a place where light and ice can create these amazing things.
Definitely awe-inspiring. We've covered a lot of ground in this deep dive, from the blue sky to deserts, from the wind to the water cycle. It's incredible how much is happening all the time right here on Earth.
It really is. And it shows how connected everything is. What happens in the atmosphere affects the oceans. What happens on land affects the atmosphere. It's all part of this web.
Okay, but there's one more frontier I want to explore, something that most people probably don't even think of as weather.
What's that?
Space weather.
Ah, yes. Space weather. It's all about what's happening out in space and how it affects us here on Earth. That's a fascinating field, really, and it can have a big impact on our lives down here.
Okay, so let's break it down. What exactly is space weather?
Well, think of it as the conditions in space that can affect Earth. You know, things like radiation, magnetic fields, those charged particles from the sun. It's mostly driven by the sun and all its activity.
Right, so like those solar flares and coronal mass ejections we were talking about before, those are part of space weather, right?
Yeah, exactly. Those are like giant explosions on the sun. They blast out huge amounts of energy and particles, and sometimes they're aimed right at us.
And those can cause some pretty incredible effects, like the auroras, right? Those northern and southern lights are something I'd love to see someday.
They are amazing. They happen when those charged particles hit Earth's atmosphere. It's like a giant light show.
But I have a feeling space weather isn't always so harmless, right? Those solar storms sound pretty intense.
Yeah, they can be. If a really strong one hits Earth, it can cause a lot of problems. Disrupt radio communications, mess with GPS, even knock out power grids.
Whoa, that's kind of scary. So is there anything we can do to protect ourselves from these space storms, or are we just at the mercy of the sun?
Well, scientists are always keeping an eye on the sun, trying to predict these space weather events. It's like forecasting regular weather, but on a much larger scale.
So there are people whose job it is to forecast space weather?
Yep. It's a whole field of study. And the more we learn about it, the better we'll be at protecting our technology and everything else from those solar storms.
It's mind-blowing to think that something so far away, the sun, can have such a direct impact on us.
It really shows you how connected we are to the rest of the universe.
Yeah.
We're not just living on Earth, we're part of this whole solar system. And understanding how it all works, from the atmosphere to the oceans to space itself, is essential.
Well, I'd say we've covered a lot of ground in this deep dive. Everything from the science behind blue skies and clouds to the power of wind, the mysteries of deserts, and even those incredible space weather events. It's amazing how much there is to learn about the world around us.
I totally agree. And, for me, what really stands out is that even the most ordinary things, the stuff we see every single day, can be incredibly complex and beautiful when you really look at them.
That's a great takeaway. And for our listeners, I hope this deep dive has inspired you to look at the world with a little more curiosity and wonder, to never stop asking questions because there's always something new to discover. Thanks for joining us, and we'll see you next time.